In this video, I am going to show you how to estimate the error or remainder of a series. So this procedure basically involves the integral test, which is why this process is called the remainder estimate from the integral test. So you'll recognize this as basically being the integral test, where you have a series that can be approximated by a function that is continuous and decreasing, and where the function and the sequence are equal for all integers greater than or equal to 1. That would be these parameters right there. So anyway, let me just real quick show you down here what is basically going on. As always, if you want a more detailed idea as to what's going on, you can read the textbook. So let's say we have a series from n equals 1 to infinity of a sub n, and that is being approximated by an integral from 1 to infinity of f of x dx. So we have a converging function. And let's say that this point right here is n. Well, this area under here can be approximated by the partial sum. Okay, so this would be s sub n, the partial sum. Well, the entire area under the curve, of course, the entire area under the curve, all of this, is the integral from 1 to infinity of f of x dx. So consequently, our error is the difference between the two. So if this is where n is, the error is represented by this area in here. It's the difference between the total area under the curve and the nth partial sum. So consequently, the way that we could rewrite that is we can say that the error or the remainder is equal to the area under the curve from 1 to infinity of f of x dx minus the nth partial sum. Well, this right here then, or actually it's going to be less than. The reason it's going to be less than, it has to do with circumscribed as opposed to inscribed rectangles. Again, for a little bit more detailed analysis on that, you can read the textbook. So this quantity here can be approximated by the integral from n to infinity of f of x dx. And so this is the basic formula that we use for all of these problems, that the remainder or the error is going to be less than the integral from n to infinity of f of x dx. All right, so let's take a look at the first problem after I get rid of some of this stuff here. So what we want to do well, let's just go up to, before I make a complete mess here, let's go up to exercise number 4. So we have the series from n equals 1 to infinity of 1 over n cubed. And so we are going to create the integral from n to infinity of f of x dx. And so the remainder will be less than or equal to the integral, where n is equal to 10, because we're looking at the 10th partial sum. So that becomes 10 to infinity. And so we create a function that looks like the sequence of the series. And then we want to integrate. Now, when we integrate this, we have an improper integral. So we have to go back to using improper integrals. And so remember, when the upper bound is infinity, we want to take the limit as b approaches infinity of the integral from 10 to b of x to the negative 3 dx. And I just wrote 1 over x cubed is x to the negative 3. So then taking the antiderivative of that, the remainder is less than or equal to the limit as b approaches infinity of x to the negative 2 divided by negative 2 from b to 10. And then I just rearranged it a little bit here, made it a little bit easier to work with. I just changed this to this. And then I'm actually evaluating the integral. We have negative 1 over 2b squared minus negative 1 over 2 times 10 squared. And so this term becomes 0 plus 1 over 200. 1 over 200 is 0.005. So our remainder is less than or equal to 0.005. That then would be our error. And that is the basic procedure. Now, another type of problem is to find the smallest number of terms needed to obtain an approximation of the given series to within 0.001. So in this particular case, we know what the error is. We need to find n. We want to find n. And so we use the same procedure, but we have a different unknown. So we start with the remainder is less than or equal to the integral from n to infinity of f of x dx. We create our function 1 over x cubed that is similar to 1 over n cubed, the sequence of the series. And then let's plug in what we know. We know that the remainder is 0.001. And we want to take the limit as n approaches b from the integral from b to n of x to the negative 3. And then we find the antiderivative once again. And I just simplified it once again. This is the same problem as the last one. And I evaluated the integral. And so this is where it changes. This is where we have a slightly different problem. We need to solve this now for n, and we have 1 over 2n squared. So multiplying both sides by n squared and dividing both sides by 0.001, we end up with this. And then it's just a matter of evaluating that. That just is equal to 500. And of course, this is n squared. Taking the square root of both sides, n is less than or equal to 22.36. And we want to round up n to the nearest integer. So n then has to be less than or equal to 23. So in other words, we would have to find s of 23, 23rd partial sum, and use it in this formula in order to get an error of 0.001. That is the basic procedure. Let's just do a couple more examples. Estimate the error in using the partial sum of 50 terms of the series. I also want to make sure that you understand you don't actually need to compute the sum of the first 50 terms. That would be very, very difficult. You'd want to use a calculator or a spreadsheet or something to that effect. We do not need to actually calculate S of 50. All right, do not need to do that. Thankfully, that would be a lot of work. Don't want to do that. All right, so again, I always start by here's my formula. I like to write formulas down. That helps me to remember them. I substitute in what I know. My remainder is less than or equal to the integral from 50 to infinity. 50 comes from here. And the 2 over x squared comes from the sequence. Well, we want to evaluate that integral. So once again, as it will always be in these problems, it is an improper integral. So the remainder is less than or equal to the limit as b approaches infinity of the integral from b to 50 of 2x to the negative 2. Evaluating or finding the antiderivative, we get this. And simplifying the antiderivative a little bit, I get this. And then evaluating the antiderivative at b and at 50. So this part's always going to end up being 0. And this is always a minus a negative. So that always becomes 2 over 50, which is 0.04. So the remainder is less than or equal to 0.04, or the error is less than or equal to 0.04. So once you know the basic procedure, these are not really difficult problems to do. Number 7. We have this series, and we want to find the smallest number of terms, once again, needed to obtain an approximation of the given series to 10 to the negative 7. That is our remainder or error. And so we are looking for n. So starting with our formula, plugging in what we know. And I should have plugged this in up there, but I plugged it in down here. So our remainder is 10 to the negative 7. Improper integral, we are finding the limit as n approaches b from the integral of b to n of 9x to the negative 5 dx. Evaluating the antiderivative, simplifying the antiderivative a little bit, and then evaluating the antiderivative at b and at n. Again, this will become 0 minus a negative is a positive, 9 over 4n to the 4th. And then doing a little bit of algebra, multiplying both sides by n to the 4th. And dividing both sides by 10 to the negative 7. We end up with this. And then taking 10 to the negative 7, putting it in the numerator as 10 to the positive 7 using our exponent rules, just to make it a little bit easier. You don't have to do that. That's just, for me, I like to get rid of negative exponents. So we have n to the 4th. So we have n to the 4th is equal to this. So n is equal to the 4th root. The 4th root of 9 times 10 to the 7 divided by 4. Make sure you do your order of operations properly. And so this comes down to 68.87, which we round up to the nearest integer. So n is less than or equal to, or n would be 69. In this case, it would be equal to 69. One more. This is similar to one of the problems in more. In fact, all of these problems are similar to the problems that you have to do in the more exercises. This one might seem a little bit more intimidating, so I decided I would throw this one in here. So you'll have something that's similar to this. So we have a series from k equals 1 to infinity of 22 times k e to the negative 0.27k squared. And we're finding the smallest number of terms. So once again, we're finding n. We're given r sub n. So we start off the same way. There's my basic formula. I plug in what I know. There's my integral that approximates the sequence. And I plug in here my error, 10 to the negative 4. And so we have an improper integral, the limit from b as b approaches infinity of the integral. And now to evaluate this integral, it almost looks like it wouldn't be doable, but you have to remember good old-fashioned u substitution. So that's what we're going to be doing here is a little bit of u substitution. I showed you the u substitution over here. Whenever you have an exponential, it's helpful to let u be equal to the exponent. I have an exponential e raised to this power. Let u be equal to the exponent, which is what I did here. I took the derivative of that, and then I solved it for dx. I then substituted in for dx du over negative 0.54x right here. And so now these x's are going to cancel out. You have 22 divided by a negative 0.54 becomes negative 40.74 e to the u, and I just substituted in what u is equal to here just to save myself a little bit of space. All right, so that is the antiderivative of the function. And so now we want to evaluate that from b to n. So here is the antiderivative evaluated at b. Here is the antiderivative evaluated at n. This, of course, is going to go to 0. And if you can't intuitively figure out why this is going to 0, you could always just graph it and you can see, aha, this is going to 0. If it's not going to 0, we have a completely different problem. And so minus the negative becomes the plus. And so we have 10 to the negative 4 is equal to 40.74 times e to the negative 0.27n squared. Well, dividing both sides by the 40.74, I have this right here. And now what do? Well, I have to take the log of both sides. We have an exponential equation to solve. That's all this is, an exponential equation. So we take the logarithm of both sides. And so that's what I did here. And then this is the power property of logarithms, where you can just bring the power down in front. This is the property that has b, the log of e to the b would be b log of e. And then the log of e is always equal to 1. The natural log of e is always equal to 1. So we have 1 times this is just this, is equal to the logarithm of all of that. And then we have to divide both sides by negative 0.27, which is what I did here, or multiplied by negative 1 over 0.27, and then take the square root. So I just left it as this big mess right here. Let's see, go to red, violet again. So n is equal to the square root of negative 1 over 0.27 times the log of 10 to the negative 4 over 40.74. Now, it looks like this should be negative because there's a negative here, but this term's also going to be negative, so it becomes positive, fortunately, because we can't have a negative square root. And so that works out very nicely, 6.9, which we then are going to round up to 7. So this involves just a little bit more work, but it's as far as the calculus goes, it is the same basic idea as the other problems. We are using the same procedure. It's just now that we're getting into a little bit more challenging integration and a little bit more challenging algebra. Nothing you guys can't handle. All right, that's it. Have fun.